Today we're going to look at Hutton's razor. So it's called like this by analogy to Occam's razor, like the smallest explanation is the most likely, right? And here the idea is to use the smallest language you can think of to demonstrate an idea when you're building a compiler or a new kind of language with new effects and so on. So Connor was helpfully pointing to another paper than the ones I've listed here, where you want to model exceptions. So you can throw an exception when you're in a bad branch. You can catch it and try to deal with the issue, and you can sequence things so that it only evaluates if the first one does evaluate to a value. Otherwise, if it blows up, the entire thing blows up. And if the first one evaluates to a value, then you do look at the second one. And again, if it blows up, everything blows up. But if the second one goes to a value, then you return a value. So yeah, minimal computation. You need some kind of base values, otherwise you can't write any programs that don't blow up. And then you can blow up, you can catch, and you can sequence. So this is the minimal, basically, language that will allow you to describe what it means to have exceptions and how they affect the control flow. Although here, I suppose there's another, catch. Yeah, the catch is doing some control flow. Right, so that's I don't know about very old, but it's a fairly old idea. It goes back to the last millennium, at least. So this is, so we tend to say this is the hello world of different type languages, in the sense that you have basically all of the bits and pieces, and it's something you cannot get to without dependent types. Or rather, I should say, the hello world part refers to the idea that we can improve the definition to root out all of the bad behaviors. And this way, we don't need to consider errors because there will be no errors. We just have our built-in invariants in the description of the toy programming language. And because our invariants are strong enough, we can guarantee that evaluating an expression will always return a value, which is really useful. So I've added some links to these things. And this is one of the oldest, I think.
Yes, I was at that workshop.
All right, let's get started. So, I mean, I've shown you what Hutton's razor is for a language with expressions, but our language is going to be even more simple than that. We won't have any expressions. However, because we're going to be looking at types and the way that well-typed programs don't go wrong, we will want at least two base types, because this is the thing we want to study. So we can have a nat that gives us a natural number. So if we have a value of type natural number, we have an expression. Maybe I should ask you what types you prefer, rather than just going ahead.
I don't know. I mean, I'm guessing you're doing addition and conditional expressions, so you need numbers and booleans.
You can do a boolean. So if we have, again, a value of type bool, then we have an expression. So far, so good. I mean, we can write like a0, which is an expression. It's a natural number, so we're going to use the nat wrapper to build an expression, and then we just have our value 0 hanging there. But we can't do very much in terms of computations, because the only thing we can do is build values. So now we're going to start adding more things in there. So the first thing we're going to add is addition. So we can add. And what we've seen so far is something of this shape, right? If you have two natural numbers, you can return a natural number. But of course, here we're describing a programming language, so it's not the case that all of the arguments to an addition are necessarily constant values that you already know. They might be arbitrary expressions. So then instead of writing nats, we substitute with expr, and that's our language construct. It's taking two arbitrary expressions that themselves will compute a NAT eventually and returns an expression that will compute a NAT. And then we have if then else. So again, what does if then else do? Oh, actually, this one is a bit more interesting, I guess. Well, not yet, but so it's taking an expression which stands for the Boolean, telling you whether you want the then or the else branch. I could actually name my arguments. That would be useful, I suppose. So these are my two natural numbers. This is my Boolean expression. And then I have two branches, and overall that builds an expression, which will have a meaning eventually. Okay, so we have a 0. We have a true, which is an expression, blah, blah, blah. It's a Boolean with value true. I have some handy patterns. I got them ahead of time because I never know which is which. Like I mean, I guess that they're just like definitions. You have the new name on the left and then the interpretation on the right. So I should remember that. And now we can write more examples. So a good sum, for instance, is an expression. And I'm going to add a 0 to if a true, then or if e. A 0 else, I should maybe make something more than interesting than a 0. A not also made one. Okay.
You could.
So I'm calling.
You could use your pattern synonym for adding.
Oh yeah, that's true.
Right.
Nope. Right.
Yes. So pregnant in the choice to call this a good sum
Yeah.
is the question, what could possibly go wrong?
So what would you call a bad sum?
That's it.
Yep. Yeah, exactly. So if you try add a 0 plus a true, implicitly, right, we're thinking in terms of the semantics of that language, and we expect it to have strong types, so it's not like JavaScript or whatever that will cast anything to anything under the hoods, and just try to be nice to you and say, okay, I'll try adding these together. Here we want to fail. We want to say, no, this is not possible. Okay.
I mean, you could, of course, play all sorts of games. Like you could pretend to be C and decide the number 0 means false and any other number means true. And you can play all sorts of games where if the Boolean false represents the number 0, and you can sort of do PHP things and make, you know, the least bad gibberish out of anything that turns up. But hang on a minute, that's just pushing garbage down the line.
Which is sometimes useful, but it's yeah, it's true that it's all about design decisions, right? So we have really strong opinions about what types are and what they should be and what typed expression should be. Of course, in existing languages, it might be a bit different. And so if you're trying to model these existing languages, you'll need to adapt the story. Okay, but for now, we have syntax describing the kind of expressions we're interested in, and now we're going to give them a semantics. So we are going to need to define what a value is. And so value is going to be a set. And I don't know, maybe I'm going to define it inductively. And I'm going to say I have a nuts. No val. And a bool interval. So if we are more permissive, for instance, we could say that all of the values are natural numbers, and then we would convert on the fly the if then else, the trues and falses into ones and zeros. But then we would give a meaning to all of these expressions, which we don't really care to have in our language. Right, so then I want to define eval. So eval goes from expressions to variables, to values, excuse me. There's not very much we can do, right? If we want to depend on the expression, we need to pattern match on it. Of course, it's picking horrible names. B and L R. Okay. Can I do this? I can do this, and then it's doing something. So for the natural number, it picked the right thing. For the Boolean, it decided to return always the natural number 0, which is not what I intended. And then for addition, it's just throwing away one of the components. So, I mean, clearly the types are not super restrictive. You can just do all sorts of things. But also there's no notion of meaning in proof search, right? Okay, so when we are here, I should zoom into that goal. Oop. If we look at the type of eval m, if I do this, we have a value, which is great. And eval n, we also have a value with the recursive call. But now we want to take the meaning of addition, which is to add these two values together. Problem, of course, is that our values could be natural numbers of Booleans. So if I recursively eval m and n, so this is the v and w, let's call them, because they're values. So this is the width with multiple expressions bundled together. I now have these two values, and I can inspect them, v and w. And now I have all sorts of crap. So let's see, that's p, let's see, that's c, no, let's see, that's n. Trying to be consistent in the naming. And then when I have two natural numbers, I'm very lucky. I just can say that the meaning of addition is addition, and I can move forward. In any other case, I need to somehow fail. And so to communicate failure, like we've seen, I think, in the very first week, I'm just going to use the maybe monad. And then this way, we just have this. We are basically taking our domain of values and throwing in an extra value, the nothing value, that corresponds to all of the trash. So we are collapsing all of the trash into a single value because we don't really care. I mean, we might care how we came to that error, in which case we will want to have more than just an extra value. But here, we're just happy to just collapse if the input expression was wrong. So in the cases where everything goes well, we can just wrap the values with a just.
You need justs on the
Oh no.
here as well.
Okay, I might as well just regenerate the case splits. Oof. Okay.
How about a catch-all?
Well, for these three one.
Yeah, well,
no,
and
for
indeed.
anything that's not, yeah, okay.
Yeah.
Okay, so we can look at just the happy path and say everything else should go to, and of course, it's not finding my value, so, and even when I do this, it's not willing to do too much work.
Well, you didn't tell it
To use plus.
to use plus.
Yeah, that's true. Okay, so that's a bit better, I guess. And then for evaluation, well, it's going to be a similar problem, right? I guess we have a bit of freedom here, but
A little bit, but not a
Yeah.
lot.
So here I'm going to be
Oof. Wow.
just x just well, no, I need to be explicit about the happy path, right? Or rather VLV then no, then and else. I'm mixing my
Yes.
metaphors. Sometimes I call them left and right. Sometimes I call them then and else. No, and
Anything else?
anything else, we're just failing. Okay. And so here, well, it will depend on the Boolean value that we get, right? But it will always succeed. So I should put the just on the outside, actually. And then if it's true, then I have VL, else I have V right.
It's a slightly peculiar conditional expression that evaluates both branches and just uses the Boolean to decide which value you want. You know.
Yeah. I mean,
Fortunately, no side effects. Like, you know, it's not like we're deciding whether to sign the peace treaty or launch the missiles. Generally speaking, if you're deciding between signing the peace treaty and launching the missiles, you don't want to do it by, first of all, signing the peace treaty, then launching the missiles, and then deciding that the right move was to sign the peace treaty.
yes. So here I was mimicking the pattern in the addition case. Oh, it was resugared. I didn't notice originally. Okay. But of course, if you don't want to be evaluating the two subterms, so in a sense, if then else is, we're saying it's always lazy in its branches. You should instead just evaluate the Boolean condition. And then based on that decision, you can decide to evaluate the left branch or evaluate the right branch.
Yeah. Right, and this is also entertaining in this situation, in this garbage-rich environment, where garbage in one branch or other of an if doesn't matter as long as it's not the branch you end up taking.
Yeah, so you can be lucky in your test suite, and then
Yeah.
it can blow up in real life. Do you want to do a bit of refactoring?
I don't know, do I? I mean, in terms of without leaving maybe land.
Yes.
But maybe just being a bit monadic.
Yes.
Or
separating the meaning of the constructor of the expression constructors from their use in the meaning function. So like here, Hutton in there is like the meaning of plus E in the value domain, right? Which is maybe val.
Mm-hmm.
But it's obscured away by this. I can do it.
Yeah.
Yeah, so as I was saying here, we're just evaluating some expressions on the fly, then doing some better matching and so on, and it's not very clear what we're doing. But what we're doing is very well behaved actually, and there's a big like design pattern behind here, behind it. The idea is that when you have your type of values, and if you have a function that expected to go from like 2 arguments to 1 result, you can just lift it to the top level and describe the meaning of that function in the value domain that we are targeting, where our evaluation function.
Before you even do this, I would be tempted to write get nat and get bool, which take a maybe val to a maybe nat.
I see.
Let's just extract.
Sure. Mm-hmm. Or a val to maybe nats?
Yeah. Depends how you want to play it.
Mm-hmm.
But yeah, you can see if you're opinionated about what sort of thing you want.
Oops. Oh, I need to wrap it, of course. And then I can have get bool. Mm-hmm. And I should change the implementation. Oh. Okay. So here we have two values, v and w. And the idea is that this expression only makes sense if our, well, this expression, that's, okay, so that's a bit complicated. They are what we call object level expressions, which are these, the expression we are talking about in this formalization versus the expressions, the AGDA expressions, which are more living at the meta level, right? So this only makes sense if these two came from evaluating an expression that eventually yields a natural number. So we can say, okay, I better get a nat from V, I better get a nat from W.
And this is where your choice to make get nat and get bool take vowels rather than maybe vowels is.
I see. Right, I mean.
It doesn't matter, or you can cook it.
Yeah, so one way to do it would be, this is to say this is maybe a value, and then insist first that
and that's
a nuts. I need to rewrap it. So here, what are we saying? We're saying first, it better be the case that evaluation succeeded. So there were not ill-typed expressions, sub-expressions in the term that made everything blow up. So I'm insisting that these maybe values are actually proper values. And then I'm using the extraction functions to say, well, okay, I got my hands on values, but now because I'm doing addition, I know that the sub-expressions should be natural numbers. So it better be the case that each of these values is a natural number. And then finally, once I extracted all of the relevant pieces by running the evaluations, unwrapping the values and seeing that I have two natural numbers, I can just return the sum of things. Which here we're just doing by doing deep pattern matching. But of course here, so, right, let me finish the refactoring. So now this becomes this. And here we're seeing the generic pattern I was suggesting, which is that we are mapping a syntactic plus to a semantic plus in the domain of the, well, the codomain of the evaluation function. And the point is that with this design, if you change the monad you're using, so we're using do notations that you know from Haskell. So in AGDA, do notation will work as soon as you have a non-ambiguous binds operation in scope, whatever its type is. It will happily disregard the block to just a bunch of binds. So it's a bit more flexible than in Haskell, but it's the same idea morally. So as soon as you have a monad, you can build something like this, and so you can use it in your evaluation function. So if you wanted to return an error message instead of just a maybe, you could just swap to a different monads, and the code would stay mostly the same. Right, I should use return here, but I'm using just.
Yes.
Right, and there's a similar story for if then else. I mean, this is where we would like to have the lazy annotation idea, right?
I think it's okay.
So morally, this is lazy, and this is lazy.
I mean, you're not going to match on it, right?
Right. But that's left to you being like a good citizen rather than. So MV, and then we have left and right. So same pattern as before. The, oops, arrow in the wrong direction. The computation of the Boolean better get to a result. That result better be a Boolean, and then branching on it using act as if then else, I can pick the computation that I like, whether it's the left one or the right one. So like that is a total language, right? So the values you get to by lazy computation or call by value computations are the same. So it's mostly implicit in the syntax here by not explicitly matching on it that this could be evaluated lazily, which is a bit annoying.
Yeah, but the fact that you're if the and then that should be eval b. Cool.
Yes.
Yeah. So the fact that you're taking maybe vals means that you are talking about computations rather than values. I think it's only when you force them that your things are values. So the distinction here we're talking about is whether if is choosing between the computations to be done or whether it's doing the computations and choosing between the values they generate. And here, because there's no forcing of L or R to be justs, we're choosing between the computations.
So I'm aligning things suggestively to point out that what we're doing is that we're evaluating sub-expressions systematically and then turning syntactic names for operation into the semantic version that actually does some computation based on these values. And so if you want to know more about this style of defining semantics, it's called denotational semantics. The idea being that you're describing the meaning of a program in a compositional manner. So you're describing what the domain of values is first. So here we made that first choice. And then for every operation, you assume that the subterms have already been evaluated. You don't get access to their syntactic representation, and you give the meaning in terms of these sub-values or values for sub-expressions. And it's a really powerful domain.
Yeah, I think it's worth distinguishing the notion of value, which is given by val, from the notion of computation, which is given by maybe val. So computation is something that isn't necessarily a value yet and might never be because it might go wrong. So what we're saying is we're interpreting the syntax of programs as the computations that those programs mean.
Right, so every expression gets a meaning as a computation, but it's not a given that this computation will go well and return a value. So we can have some examples here.
Indeed.
So let's do it like this. So that's a trick I like to use. So eval a0. Oh, wrong equal sign. So if you use REFL in the goal, if you remember, REFL, the only proof is that the left-hand side is equal to the right-hand side. So that goal is already solved. It's known to be equal to the left-hand side. But then if you do the Control U, before Control C, Control S, solve. It will actually show you the normal form of that solution that you found. So that's a cheap way to get the evaluator to go all the way and also to record the answer in the file. Because you can always do like evaluation here in the small bar at the bottom. Okay. First of all, you need to remember the good combination, yeah. And then if you do it, you get the value, but it's transient. It's not recorded in the document. And so if you change something somewhere that actually breaks the semantic you intended, you don't have that check, that unit test still in the file. So I'm not going to eval a bool because it's kind of boring, but I'm going to eval a good sum. Give me something here. Raffle. I think a good sum was fairly boring. It was 0 plus if true, then 2, else 1. So it's a good thing that we're getting 2. And then we can eval a bad sum. Which was 0 plus true. And unsurprisingly, this goes to nothing.
Yeah. But now you can write an if which has a bad sum as the branch not taken.
Oh, yeah, yeah. I was going to eval a bad f also.
Worth doing.
A bad f is branching on 0. And we've insisted that branching was always on Boolean, so this goes to nothing. Right, and now we have this thing. So eval if e a true, else then maybe first a 0, else a bad sum. This is what we wanted, right?
Yeah.
So via REFL. And yeah.
This is showing that we were choosing between the computations, not between the values, because otherwise that would have failed.
Mm. Yeah, we're only checking along the path that the evaluation is exploring, which means as long as we're not taking the wrong branch, we're happily moving along, but it might blow up in our face at some point in the future, which is not ideal. And so that's why we have typed expressions. Okay, let's do typed expressions. So the idea, I mean, the main issue here is that we have a single type of expressions, and we don't distinguish between an expression that computes a natural number and an expression that computes a Boolean. And then when we're adding, we have no invariant telling us what, how we came to that expression. And of course, we may have built it the wrong way. So the trick here is to define a type of types, but a type of types for our small language. So it's going to be a small set, and we're going to have the type of nats, or maybe I should call it nats type, or maybe I can just.
I would. Yes, fine.
We can have natural numbers, and we have Booleans also. I'm using backticks to mean that it's syntax rather than the meaning in natural numbers.
So with the idea that it's sort of like a quotation mark.
Yes.
We're saying, you know, this is the thing that says nat, which we then interpret in a moment.
Yes, and then I can copy paste my previous definition. I can replace all of the expers with T exper. Oh, exper T exper. Boop, 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 boop. Now if I try to reload, oh, it still works because I haven't changed the type.
Yeah.
So now what I want to say is that it's actually defining a family of expressions which are indexed by the type of the value being computed by the expression. Okay. So now every place where I have a T expert, I need to explain what its type is. So if I have a natural number, it shouldn't be too surprising that the type is not. If I have a Boolean, it's a bool. If I have an addition, then it better be the case that both sub-expressions are natural numbers, because otherwise I will crash. And the overall thing will be a natural number itself. And then finally, when we have an if then else, well, the conditional is a bool, but then we have a bit of freedom on what to do with the left and the right branch of the if then else. So what should we do here?
I think you should be allowed to use if then else to choose between computations that are compatible.
It's a possibility. Yeah, we can say full sigma. We tend to use sigma and tau for types, but whatever. I guess I could be.
I think further down
call it
I think you use capital T at some point.
Oh,
you might as well.
That's terrible.
That's,
Okay. So if I'm saying this if then else overall computes a T, it makes sense that no matter what the Boolean branching between the branches says, I should get a T. So both of them should be computing a T. Of course, in Agda, you know that it can be different, right? It can be that the T can depend on the value of the Boolean.
I mean,
so you can distinguish between the true path and the false path. But here we just have simple types. So
yes,
it seems reasonable to just be
so
polymorphic.
It is one of those things about the type systems we often find in programming languages, that you have this if then else thing, and you know, we generally use a conditional because it's important to decide which of the two branches to take. So it's kind of weird that the types of the two branches in no way bookkeep the importance of the condition. I mean, isn't it strange, you know, that this is, that there's the condition is testing whether it's safe or appropriate to do something, and none of that contingency is showing up in the types. I mean, it's actually frightening. I mean, tell you what, here's a thing you can do in most programming languages. You take a program which compiles, you know, gets through the type checker, and then you swap the then the else branches of every single conditional in the code. Do you know what? Your code will still compile. Won't bloody work, but it will still compile. And that's alarming.
Right, so
I mean, we could even write that.
That transformation, yeah.
Type safe transformation on this.
Yeah.
But anyway,
Yeah.
let's not. Let's go with the happy path. We've got 10 minutes of science.
Yeah. So what I wanted to say though is that here we've made the type implicit, and it's actually sitting there, meaning that when you're consuming such an expression, you could actually look at the type and have a different behavior in the if then else, depending on the type. This is maybe not what you want. Like, this is a bit weird, I think. So one thing you could do, and this is going into more advanced type theories, is use an extension called erasure that allows you to say that T here should not actually be available at runtime. You need to mention it because it's showing up in the indices. It's constraining what the type should be, in particular saying that these two branches should be computing something of the same type. But I shouldn't be able to branch on it to decide whether the F should behave one way or another. So I'm going to remove this, but just as an aside, when you want to express the idea that some things are there just for invariance and should not be inspected, you have this ability by using a different type theory again. Okay. So now we can write typed expressions. So let's do another a good sum best. It's no, that's not what I want to do. I'm just getting confused. So it's a good sum, so it should be an expression of type that computes
It's a
an
text
at.
burr, not a tie expur.
Oh, yep. Up. Okay, so it's giving me something. Oh, I haven't introduced the patterns here.
You should still be able to use the old pattern synonyms, I think.
Oh yeah, the names are the same. Yeah, that's true.
Pattern synonyms are extremely shallow.
Thank you.
Or are they? That's it.
Very strange. What the heck? Yeah, I thought they were purely syntactic. I don't know what the heck.
Maybe
is going
somebody's
on.
been fiddling around in the back of the room.
Yeah. Okay. Well, let's not do that then. So we have a good sum best, but then if we try to write a bad sum, or I should still call it best because the other one is in scope, where we had 0 to
You need
true.
a bool true. A bool.
Oh, cheers.
Yeah.
And here we're getting a type error, just telling us that bool is not the same as nat, and therefore we're expecting a type expression of type bool, and we got one of type nat.
It's kind of cool
It just rejected.
that the Agda just does type checking for our little toy language.
Under the hood. So now we cannot write this thing, which is good. Right, and so for evaluation, I think we have time.
We have.
It's super quick, right?
Yeah.
So again, your first instinct should be, well, what's the domain of values that we're going to target with our function? And now, because the type of expressions is indexed by this inductive, well, it's not very inductive, but type, the domain of values is also going to be indexed by it. I mean, you could throw away that argument, but you would have strictly less information, which is not ideal. And I'm going to define it strategically as a function, because I could define it again as a data type, but then I would need all of my functions that are going into the data type to grab the value to extract it. But here, from the tag tie, we know exactly what the value should be. So if we're computing something of type nat, it will give us a nat, a proper nat, and something of type bool will give us a proper bool. And then we can define t-eval, which is a function which for any type expression of type t will return a type value of type t. And so again, we're just case splitting. We might have a little bit more chance here. Okay, not too bad. So if we have a natural number, we return it. If we have a Boolean, we return it. Because the t-val, right? When you matched on a nat, you learned that t was nat. So t-val computed to nat, which means you can directly return the value. Same for Boolean. For addition, again, it's really eager to throw away half of the computation, but you can just apply the plus function on natural numbers to the sub-expression, the two sub-expressions that have been evaluated, because you've learned that both of them were of type nat, meaning the values are proper natural numbers, and so you can just apply addition directly, and it will give you, again, a t-val, an appropriate t-val. And then let's quickly rename this. If then else, what are we going to do? Well, same thing again. If we t-val the b, then that gives us a Boolean on which we can branch immediately without using getBool or whatever. And then we can pick between the tval L and tval R computations based on the actual Boolean value that we computed. So now we don't have any errors anymore because we've enforced in the syntax itself the idea that we can only build computations that are well-typed by construction. So we don't need that maybe monad anymore, and everything is clean and just computes directly. And so we can write our examples again. So if I tval a good sum best, should get 3, I think. Oh, there's a different sum.
0.
0 plus 1. Yeah, okay. Which is 1. And I think it's a good place to stop.
Yeah, I guess just looking around the corner, we're in the business of asking how we get our hands on terms that are known to type check. If we start from expressions that might be rubbish.
So user inputs.
Yes, what's the process to either turn them into well-typed terms or reject them?